For decades, this symmetry seemed impossible. In a real crystal, it was forbidden. But forbidden matter still found a shape. Look at the star in this pattern. It turns by 5 equal steps. Yet it does not fall apart. Here is the paradox. Math allowed the fivefold star. Physics seemed to forbid the crystal. How can matter obey both? The answer begins with repeat. Repeat is the old rule for crystals. Break repeat, and order changes. Normal crystals are periodic. Periodic means a shift changes nothing. Slide the pattern by 1 cell. Every atom lands on an atom. The crystal keeps a steady beat. That beat makes order easy to read. Now watch the allowed turns. A line can turn 2 ways. A triangle can turn 3 ways. A square can turn 4 ways. A hexagon can turn 6 ways. Each turn fits a repeating grid. 5 is the problem. Fivefold symmetry means 5 matching turns. Each turn covers 1/5. It makes a clean star. But it cannot fill a repeating grid. The angles leave gaps. So far, repeat gave crystals their law. Now the rule changes. In 1974, Penrose drew tiles. A Penrose tiling covers a flat plane. It uses strict shapes and edge rules. The tiles grow without a repeating shift. The pieces look simple. One is a kite. One is a dart. Their edges carry matching rules. Matching rules say which edges may touch. Small marks control the whole floor. This floor is aperiodic. Aperiodic means ordered, but not repeating. Local patches return again and again. Local means near one chosen tile. But no slide matches the full floor. Order survives without repeat. The fivefold star now has a home. It does not need a normal grid. It can live inside aperiodic order. The visual effect is strange. Stars repeat as echoes. But their positions never form a beat. Here is the trick. The drawing was not just decoration. It showed another kind of order. If tiles could do this, could atoms? For years, many scientists said no. Then a microscope image said yes. In 1982, Dan Shechtman looked closer. He studied an aluminum alloy. An alloy is a mix of metals. His sample made sharp diffraction spots. Diffraction shows how waves scatter. It reveals hidden atomic order. The spots showed fivefold symmetry. That should not happen in a crystal. The image had clean order. But it lacked the normal repeat. It was not noise. It was forbidden matter. Scientists expected a lattice. A lattice is a repeating atomic grid. Move it by the right distance. The same arrangement returns. Shechtman's sample refused that move. The pattern would not snap back. Now the rule changes again. The new word was quasicrystal. A quasicrystal has order without repeat. Its atoms are not random. They follow a strict pattern. But the pattern never shifts onto itself. That is why Penrose matters here. His tiles gave a visual language. They showed fivefold order could grow. They showed repeat was not required. The crystal idea had been too narrow. Nature had used a wider rule. The resistance was fierce. Linus Pauling mocked the discovery. He called Shechtman a quasi-scientist. The insult missed the point. The pattern kept being measured. The evidence kept returning. So far, the image survived doubt. More labs found the same order. The forbidden crystal became accepted. In 2011, Shechtman won the Nobel. The prize marked a changed definition. Crystals no longer needed repeat. Now compare 3 worlds. Random has no reliable rule. Periodic has rule and repeat. Quasicrystal has rule without repeat. That middle place is the lesson. Order has more than one shape. The concept is simple now. Draw a rule. Let it grow. Watch what returns. If everything repeats, you have a beat. If nothing returns, you have noise. But if forms return without a beat, another kind of order appears. This is why the discovery matters. It changed what matter could mean. Forbidden matter was not impossible. It only refused to repeat. The opening paradox was never broken. It was too small. Order was always there. It just refused to repeat.